Okay, last point I want to make here: capacitors in series and parallel. Let's start with, I'm going to go with parallel first. Capacitors and charge. So what happens when you have capacitors in parallel with a certain charge, or how does the charge distribute? So we have capacitors like this. This will be capacitance 1, capacitance 2, and blah blah blah, and they are equivalent to a C12. Okay. Now we said components in parallel split charge, and so if these two guys are charged up, let's say if this guy is your equivalent capacitance, and you calculate he will have Q12 for the total, then that'll split up into Q1, Q2, and you'll have Q12 equals Q1 plus Q2. Okay, that's not hard to see because you're going to have some positive charge accumulated on the top plate here, plus Q12, right? And that's going to split into plus Q1 and plus Q2. I mean, that makes sense. And then you'll have some negative charge on this guy and negative charge on this guy, which will be like a total negative charge on that guy. Okay, so the parallel case is not hard to understand. It's the series case that I think gets people confused. So when we talk about capacitors in series, let's have two capacitors. Okay, C1, C2. And you have charge on both, Q, Q. It's the same charge. And if you have C12, an equivalent capacitor, that's subject to the same voltage as that pair, it's the same as the charge that would be on the equivalent capacitance. So let me make it clear here. We're talking about an applied voltage V there, and also an applied voltage V there. Okay, so why does that happen? Well, here's the thing. So you imagine that you have your capacitors here. The top plate of this guy, okay, so this guy here, the top plate of this top capacitor should behave like the top plate of this capacitor, of your equivalent capacitor. And then, let me pick a different color here. Let's see, let's go with the baby blue. Okay, the bottom plate of capacitor 2 should behave like the bottom plate of this guy. Okay, which means, okay, so if this guy has plus Q on top, and let me just erase this, then this guy, come on, brush, there we go. Okay, this guy should be plus Q on top, right? Top plate equals top plate. Down here, minus Q on the bottom and minus Q, okay? So your equivalent capacitor has plus Q and minus Q. Easy enough. When you translate that into the actual capacitors that are there in series, though, what does that mean? Well, it means this plate has minus Q, this plate has plus Q. Now, in the middle, you've got the bottom plate of the top capacitor and the top plate of the bottom capacitor, and these are linked up, okay? But they can't get charged from the outside world. So look here at this black line and this black line and this stuff. This is all connected. They can share charge in this area between these two inner plates and the wire. They can do whatever they want with charge, but they cannot get charged from the outside world. Now, capacitors will not. Capacitors can't have different charges stored in each plate. It doesn't happen. Okay. So what that means is this capacitor will not be happy with plus Q in the upper plate unless he gets minus Q on the lower plate. And if he gets minus Q on the lower plate, then he must have done that by taking his charge, some of his positive charge, and shoving it down to this plate here of the other capacitor. So this capacitor must now, or this plate must now have a residual charge of plus Q, which very conveniently balances the minus Q on this lower plate. But what this means is, this is why capacitors in series will have the same charge, and it will be equal to, and I'm putting an exclamation point because it's important, it'll be equal to the charge on an equivalent capacitor. So if you wanted to label these Q12 as the equivalent capacitor charge, then what you would say is Q12 is equal to Q1, and that's also equal to Q2, okay? Where Q1 and Q2 are your charges on these guys, okay? And I'm putting exclamation point. That's not factorial or anything. Don't pull that weird math stuff on me, but I'm just doing that to say, yes, it's true, okay? So that's why capacitors and series have the same charge. If you get this far and you want to figure out, let's say you want to figure out what the voltage change across each of these two capacitors is. So let me just move this guy over and, excuse me, Mr. Series Diagram, I'm just going to steal some of your space. So I know the total voltage change across these guys. Let's say I figured out what Q is, and I want to find the voltage change across 2, and that's supposed to be a 2, V2, and the voltage change across 1. Okay, this is, this is getting ugly. Let's say once I figured out Q, and Q equals this, then all I have to do to find V1 and V2 is then take, well, I'm out of space there, so I'm going to do it up here. My scroll bar is all the way down, so I don't have any more space in this little painting drawing. But what I do is I take Q equals CV and apply that twice. Now that I know the charge on each of these, which I figured out by going through this, I say this Q must equal C1 V1. Okay, so V1 here is going to be whatever my net charge is, or my total charge is, divided by C1, and then it's also going to equal C2 V2. So I can use that to figure out these voltages here. One final thing is terminology here, and some people may be thinking, well, you've got Q charge stored on 1 and Q charge stored on 2. Why isn't that 2Q? Why isn't this value here twice this value, or this value plus this value? Because you're storing charge on this guy, storing charge on this guy. Doesn't that count as twice the charge? No, it doesn't. The reason why is because what we're talking about is the charge stored on an equivalent capacitor. So C12 is meant to be equivalent to this combination. What that means is, to the outside world, if a voltage V is applied to this combination and a voltage V is applied to C12, it should look exactly the same. What the outside world sees is how much charge is stored on this capacitor, or sorry, on this plate, and how much charge is stored on this plate. And they should be opposite, signs, equal magnitudes. What the outside world sees here with this combination is the charge on this upper plate and the charge on this lower plate, which should be opposite signs, equal magnitudes. Okay, so as far as the outside world is concerned, this is all internal to this combination. This doesn't really count as stored charge, because this is all stuff that was inside this group anyway and is never coming out. This plus Q and this minus Q here, this does not count as stored charge, because it will never leave. We can't get it out, we can't put more in there, so it's not stored. It's just staying there. Stored implies we could get it out sometime if we wanted, but it's not stored. So that's why we say that this stored charge here is equal to the stored charge here is equal to the storage charge here. Even though it may appear, if you take the total charge stored on each of these capacitors, that's more, but that's not correct, because the charge stored on the unit is just Q. Okay, hope that helps, and that is really all the yakking I'm going to do because I'm hungry. Good luck.